Okay, the first example on the second page here is about the area of a circle. This says the area of a circle is directly proportional to the square of its radius. So area of a circle here is, we're going to represent that by a capital A. That's area. Area. Now it's directly proportional. Okay, that's just going to be a constant multiple. But then it says the square of its radius. Okay, so I included this one because it's not just direct proportional to like a single other variable. It's directly proportional to something that's been done to that variable. So in this case, the square means r squared. It's raised to the power 2. And that's where r is the radius of the circle. Okay, so the equation is going to look like a is a constant multiple of r squared. Why did I put parentheses? I didn't really need to put parentheses. Let me rewrite it without parentheses. A is k r squared. By the way, I think it would be irresponsible of me not to mention that the value of k is this number pi, which is about 3.14 ... That's the number pi. So in this case, pi is the special constant of proportionality that describes the way area and the radius squared are related to each other. Okay, so let's answer this question. If you double the radius of a circle, by what factor does the area increase? Okay, well, let's find out. Let's say the area originally is kr squared. Okay, now let's say you're going to double the radius. I'm going to write k, instead of kr squared, I'm going to write k times 2r squared. So I have to replace the r with a 2r. So I'm doubling the radius. Now, when you double the radius, you have to make sure you put it in parentheses because we're supposed to be squaring the radius. So now we're squaring the doubled radius. You have to put the parentheses in there to override the order of operations and make sure we square that entire expression. So, okay, what do we have now? Well, if you square the 2, you get 4. And if you square the r, you get r squared. So we have k times 4r squared. You can rewrite this as 4kr squared. But kr squared is the original area. So this is 4a. So what we can see here is that the area increases by a factor of 4. Okay, area increases by a factor of 4 when you double the radius. So that's kind of cool. So now for these next three, I just have these as examples of other types of situations where variation comes up in science. Now I'm just gonna express these, express the equations. I'm not gonna go through like example problems, but you certainly could make up a problem where you have several pieces of information and you solve for a third one or something like that. So let's talk about them. So this first one is the inverse square law for light. It has to do with light intensity, right? That's basically how bright is the light. Well, as you get farther away from a light, it gets less bright. It appears to be less bright when you look at it, right? Like if you look at a light that's really, really far away, like for example, a star, its intensity is very low, right? It's just a tiny point of light. Whereas if you were to look at that star very close up, it would blind you, right? So intensity is going to be represented by the variable I, capital I for intensity. And it is inversely proportional to the square of the distance from the source. So this is a constant in the numerator, and then we're dividing by the square of the distance. So this is the rule that has been experimentally verified by scientists. This is the rule that describes how light intensity decreases as you move farther away. Remember that inverse variation is where if one increases, the other decreases. So if distance increases, the intensity is going to decrease. That's that motion, right? That motion, if it's on the right and the left, whatever. Anyway, that's how it works. For other types of physical phenomenon, you sometimes have an inverse cube law. So I think, and I might have to double check, you might have to double check me on this, but I think for sound, when sound travels away from a source, I think it decreases its intensity, but it decreases more quickly, proportional to the inversely proportional to the cube of the distance. I think I might have that one wrong. I might be thinking of gravity, but they both react in sort of similar ways. Anyway, the next one I want to talk about is the ideal gas law. So ideal gas law is basically how gases, their pressure, their temperature, and their volume all work together. Oops, excuse me, sorry. If you heat up a gas, it tends to expand in volume because the molecules are moving around faster, so it kind of gets bigger. Whereas if you contain it in a fixed volume, then instead of getting a bigger volume, it's going to just exert more pressure on the container, right? Because of the molecules moving around and bouncing faster and harder against things. So there's this relationship that describes how pressure and temperature and volume are all related. It says the pressure of a gas, P, varies directly with its temperature, so direct variation, so K multiple of the temperature T, and also inversely with its volume, so divided by V. So this means that if you increase the temperature, that is going to increase the pressure, unless you hold the pressure constant, in which case increasing the temperature will increase the volume. Now instead, if you increase the volume, then that can actually decrease the pressure, unless you're holding the pressure constant, in which case somehow you would increase the volume and decrease the temperature. So it's sort of like all sorts of different combinations and like relationships. If you fix one of the three variables, then this describes how the other two are related to each other. So that is a useful one that people use in physics and chemistry. And then the last one is the gravitation law. This is called Newton's universal law of gravitation. Isaac Newton was the first person to figure out this law, and it has been experimentally verified tons of times by physicists as well. And it says the gravitational attraction force between two point masses, so that's like the center of gravity of one object and the center of gravity of another object, that force of gravity is directly proportional to, so a K constant multiple of, the product of their masses. So that's, product means multiplied together, so it's the mass 1 times mass 2. So that's like joint variation. It's directly proportional to two different things and their product. But then it's also inversely proportional to the square of their separation distance. So divided by the square, d squared, of the distance between them. So that's like when you have the sun over here. Let's draw a sun. And its point center of mass. And then over here you've got the Earth. Right? That's, here's the Earth. And its center of mass, then the distance between them is right here, distance. And the force of gravity on the Earth that's felt the force of gravity between the Earth and the Sun that causes the Earth to stay in rotation around the Sun, in revolution around the Sun, that is determined by this formula. It depends on the mass of the Sun, mass of the Earth, and how far apart they are. So, I think that's all the examples. That'll do it for this chapter.